In previous videos, we looked at equilibrium from a quantitative perspective, looking at the equilibrium concentrations and the equilibrium constant. We've also looked at the value of the equilibrium constant to tell us something about whether the reactant or the products are favored at equilibrium. In this video, we're going to introduce one of the most important principles in chemistry, especially related to equilibrium. That is Le Chatelier's principle. We'll use Le Chatelier's principle to help us understand in a qualitative way what happens when a system is no longer at equilibrium. In short, Le Chatelier's principle says the following. If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift to counteract the effect of the disturbance. Let's look at how Le Chatelier's principle applies when we change the concentration of a reactant or product. If a system is at equilibrium and the concentration of a reactant or product is increased, the reaction will shift to consume the added substance. However, if the concentration of a reactant or product is decreased, the system will shift in the direction that will produce more of the substance that was removed. This image demonstrates Le Chatelier's principle when it deals with changing the concentration of a reactant or product. We represent the reaction of N2O4 producing two NO2 molecules. In the first square, we see that we have an equilibrium concentration of NO2 and N2O4. And then we add some NO2 molecules to the system. Once the NO2 is added, the system is no longer at equilibrium. What's going to happen since the system is no longer at equilibrium? As the second square shows, the system will move in the direction that will consume some of the added NO2. This way, the reaction will shift from more NO2 on the product side to produce more of the N2O4 on the reactant side. Let's see if we can use what we just learned to make predictions. In this question, we're given the system 2 NO gas reacting with 1 mole of O2 gas to produce 2 moles of NO2 gas. And we're asked, which direction will the system shift? First, if O2 is added, or second, if NO is removed. In the first situation, we're adding O2, which is a reactant. Le Chatelier's principle says the system will shift to counteract what we did, or to remove O2. Since we added O2, the system will try to remove O2 by shifting to the right, to use up O2 and produce more NO2. What about the second example, where NO is removed from the system at equilibrium? If NO, a reactant, is removed, the system will shift to the left to produce more NO and to decrease the original concentration of NO2. When we look at Le Chatelier's principle as it applies to a system in equilibrium, which has a volume or pressure change, it's important to remember the relationship between volume and pressure. In short, reducing the volume of a container is the same as increasing the pressure in the container. If we reduce the volume of a container, this will cause the system to shift in the direction with the fewest moles of gas. Let's look at an example of Le Chatelier's principle in changing pressure. In this image on the left, we have nitrogen and hydrogen molecules reacting to form ammonia, or NH3. In the image on the left, before the cat jumps on the cylinder, we have 9 moles of gas, with 1 mole of NH3 2 moles of N2 and 6 moles of H2. Once the cat jumps on the top of the canister and compresses it, increases the pressure or decreases the volume of the container, we see that the system has shifted. Now there's 3 moles of ammonia, the product, only 1 mole of ammonia, and 3 moles of hydrogen. This agrees with what we mentioned previously. If we reduce the volume or increase the pressure of a system, the system will shift in the direction with the fewer moles of gas. In the second image, we only have 7 moles of gas instead of 9, and this is an example of Le Chatelier's principle in terms of changing pressure. Let's look at an example to see how to apply this version of Le Chatelier's principle. We're asked what will happen if the volume of the container is increased or if the pressure of the system is increased given the same equilibrium system we used in the previous problem. Let's look at the first question. If we have an increase in volume, that means that we would have a decrease in pressure. An increase in volume means that the system has room for more moles of gas. In the equilibrium system, we have 3 moles of gas on the reactant side and only 2 moles of gas on the product side. Since we increased the volume, we have room for more moles of gas, so the system will shift to the left to produce more moles of gas. In the second example, instead of increasing the volume, we're now going to increase the pressure. As we saw in the cat example, when we increase the pressure, we're essentially decreasing the volume, and the system will shift in the direction with the fewer moles of gas. In the system we're using, we have 3 moles of gas on the reactant side and 2 moles of gas on the product side. So if we increase the pressure, the system will shift to the product side. It will shift to the right to decrease the moles of gas present. When we look at changes in the temperature and how they affect an equilibrium system, one thing that will be very different from the other changes is that a change in temperature will change the equilibrium constant for the system. When we change concentrations of reactants or products, or when we change the volume or pressure of a system at equilibrium, there is no change to the equilibrium constant. When we change the temperature of a system at equilibrium, the effect of the temperature depends on if the reaction is endothermic or exothermic. When we have an endothermic reaction, that means heat is added to the system. In other words, we could treat the heat as if it were a reactant. For an exothermic reaction, heat is released from the system, and so we can treat the heat as products in a reaction. Viewed in this way, heat can be treated as either a reactant in endothermic reactions or product in exothermic reactions. Since Le Chatelier's principle says that added products will shift reactions to the left and adding reactants will shift reactions to the right, we see that increasing the temperature will increase the value of the equilibrium constant for endothermic reactions, and increasing the temperature will decrease the value of the equilibrium constant for exothermic reactions. At the same time, increasing the temperature in an endothermic reaction will shift the reaction toward the products, which will result in a larger equilibrium constant. Increasing the temperature in an exothermic reaction will decrease the value of K by shifting the reaction toward the left, or toward formation of more reactants. What will be the effect of adding a catalyst to a system at equilibrium? In short, adding a catalyst will have no effect on the composition of the equilibrium mixture. The catalyst will increase the rate at which the system reaches equilibrium, but the equilibrium itself is not disturbed by the presence of a catalyst. Let's take a few minutes to summarize everything we've learned based on Le Chatelier's principle. We'll look at an increase in the reactant concentration, the pressure, or temperature. We'll predict which way the system will shift, and also what the effect on the value of the equilibrium constant will be. If we increase the reactant concentration, the system will shift to the right, and the value of the equilibrium constant will remain constant. If we increase the pressure of a system in equilibrium, the system will shift in the direction of fewer moles of gas, and the value of the equilibrium constant will again remain constant. If we increase the temperature of a system in equilibrium, the system will shift right if the system is endothermic, and in that situation there will be an increase in the value of the equilibrium constant. However, if we increase the temperature of a system at equilibrium and the system is exothermic, the system will shift to the left and we'll see a decrease in the value of the equilibrium constant.